Right, we've been talking about different vector spaces. Now we're going to go back to our familiar vector space of column vectors. And with this new concept of basis, we're going to revisit some things that we've looked at before. Now really, basis is just a linearly independent spanning set. And we've done that before. We've looked at column spaces and found a linearly independent spanning set. We've looked at row spaces, we've looked at null spaces. So we're really not going to do anything new. We're just reinforcing concepts that we've done before. Okay. Remind you of some theorems here. Row equivalent matrices have identical row spaces. So that's how we get a row space. We row reduce and take the rows of the reduced matrix. Theorem BRS says the non-zero rows of a matrix in reduced row echelon form are basis for the row space. Okay, so we're going to use these row reduction operations to find bases. Okay, so here's a set of vectors, and this is kind of a familiar computation. If we want to find a linearly independent spanning set that spans the same span that these do, let's turn these vectors into row vectors, row reduce, and we obtain two non-zero vectors. And if you take these vectors, consider them as column vectors, these column vectors will have the same span as the four vectors here. Furthermore, these two vectors are linearly independent. Now to make this look nicer, you can multiply these vectors by constants that won't change the span. So here's a nicer way to write two linearly independent vectors that span the same span as the four vectors, as I've shown before, as these four vectors that were originally presented. Okay, well here's another example, just very similar. You have four column vectors. To find the basis, you turn them into row vectors. See, the first column becomes the first row here. You row reduce, and then you consider these rows as column vectors. These become the basis for the original set of vectors. And you can multiply through by 17 to get a nicer looking basis. Now let's move right into this section. We've seen that the columns of a non-singular matrix are linearly independent. So in fact, these columns are linearly independent, and certainly the columns span their spanning set. So the columns of a non-singular matrix form a basis of the column space. So let's formalize that statement. Suppose that A is a square matrix of size m. The columns of A are a basis of Cm if and only if A is non-singular. All right, so look at the condition here. A is square, so same number of rows as columns. So there's actually m vectors, m columns, and each column has m components. In this case, it turns out that those m columns in that non-singular matrix form a basis for all m-dimensional vectors. Okay, so since this is a proof of if and only if, we have to show two things. We have to show that if the columns are a basis, then A is non-singular. On the other hand, we have to show if A is non-singular, then the columns form a basis. All right, so we go the first way. If the columns are a basis, now basis, one of the requirements of a basis is that the vectors be linearly independent. If the vectors are linearly independent, then we know that the matrix is non-singular. Okay, you can look back there at that theorem. Theorem NMLIC, which says A is non-singular if and only if the columns of A form a linearly independent set. That's true for a square matrix. Okay. All right, so we've gone the first way. We've shown that if the columns are a basis, then A is non-singular. Let's go the other way. Suppose A is non-singular. Okay, if A is non-singular, by the same theorem, the columns are linearly independent, And then we have another theorem that says for a non-singular matrix, the column space is equal to all of Cm. All right, let's look at that theorem just to verify. Okay. Suppose A is a square matrix of size n, then A is non-singular if and only if the column space is Cn. So you can review that theorem. We've looked at that before. So we have it. So we have, if the columns are linearly independent, if the matrix is non-singular, then the column space is all of Cm. So we have a linearly independent spanning set for Cm. So very good way of finding a basis for Cm is take the columns of a non-singular matrix. Okay. All right, so for example, if we have a matrix here and you find out that it is row equivalent to the identity, that means it's non-singular, so the columns automatically form a basis. All right, so the final conclusion here is that we have all of these statements that are equivalent to the fact that A is non-singular. And here we can add one, that the columns of A form a basis for Cn. Okay, just run through these quickly and remind yourself of these properties. A is non-singular if and only if it row reduces to the identity matrix, if and only if the null space contains only the zero vector, if and only if the linear system LS of AB has a unique solution for every possible B, if and only if the columns of A are linearly independent, if and only if A is invertible, if and only if the column space of A is all of Cn, if and only if the columns of A form a basis for Cn. Okay.